Thanks, Amit. And let me start with a high-level motivation and statement of these results. So let's say you would like to design an algorithm for some statistical problem, where by statistical problem I mean any problem in which you model your input as coming ID from some unknown distribution D. And the goal of the algorithm is to learn something about the distribution D. And you can pick your favorite problem. So let's say you imagine that you've tried for a while and you failed, you can design an efficient algorithm, so you suspect that this is a problem which is computationally hard. But of course you would like to prove it. But the question is, how do you do it? You don't really know how to do it, you're working on learning theory, but luckily you have a complexity theory friend, so you call up that complexity theory friend, you explain to him your problem and ask for some techniques to analyze the computational complexity of a problem. Unfortunately, as the complexity theory friend will explain to you, despite decades of research, we still don't have good techniques for proving lower bounds on computational complexity. And in a way, the main techniques for showing some sort of evidence of hardness is via reductions. So you basically find some problems that other people have tried to solve, and you reduce from that problem to your problem, and it gives some evidence of hardness of your problem. Reductions are, of course, great. We love them. But more often than not, you won't be able to find the problem that has been already well studied, and you can reduce from that problem to your problem. And the question is, what can you do in this situation, which is, I would say, a relatively sad state of affairs in understanding of computational complexity? So in this work, we'll look at a different approach, which is based on an oracle model, referred to as statistical query oracle. And this model does not restrict computation, but it restricts the way you access the data. Instead of accessing the distribution through observing the samples, the algorithm will be able to interact with this oracle by asking queries about the unknown distribution. And I'll define what these queries are. And the important property of this model is that it captures many of the most powerful algorithmic tools which are used in statistics and machine learning. At the same time, as we'll show in this work, there exists a notion of dimension that for any statistical problem, think of any, will tightly characterize the complexity of solving that problem in this model. And importantly, this dimension is relatively simple. And what I mean by this, it doesn't involve any computation, doesn't involve any dynamics, interaction, nothing, just some linear algebra and a couple of quantifiers. So basically, you can actually just go ahead and compute it. There are some problems for which computing it might be relatively hard, but you can just ask Ohad and he will help you. So at the end of the day, we get a dimension which we can analyze without having to solve P versus NP problem in the process. And at the same time, it captures the power of the algorithm we most care about in machine learning. So now let me go to give you a bit more details about this whole approach. So as I mentioned, we'll be looking at problems where you would normally think of your input as consisting of IID samples from some distribution D about which you want to learn something. Here we'll be looking at the model in which the algorithm, which is the statistical query algorithm, will interact with an oracle, first defined by Michael Kearns in '93. And this is an algorithm can ask a query to this oracle, and a query to this oracle will be described by a function which maps an element of your domain to some value we normalize to be in the range -1, 1. And to such a query, the oracle will respond with some value v, which is within tau close, where tau is the parameter of the oracle, of the expectation of that function with respect to the unknown distribution D. Where you can think of this accuracy or tolerance parameter tau as roughly corresponding to 1 over square root n samples in the original model. So, for example, of the things you can do with such queries, for any event, if you define a function to be the indicator function of that event, then the estimate of the expectation of this function will give you an estimate of the probability of the event. And if you choose your function to be a loss of some hypothesis on a certain point, the oracle will give you an estimate of the expected loss of that hypothesis on the unknown distribution. So after observing one response, you can actually ask additional queries, as many as you have time for. So that's the basic model. Let me also mention that it was known in other communities. For example, in data, this type of questions about the data is studied under the names of counting queries and linear queries in database community, and as linear statistical functional estimators in statistics. So the main reason why this model is studied is a variety of applications, and you can think of those applications as coming from this simple observation that once you kind of abstract away access to data, you can implement this oracle with many additional constraints or desirable properties. So the original, for example, the original motivation of Kearns was to design noise-tolerant algorithms, and you can convert any statistical query algorithm in this model to a noise-tolerant algorithm from specific types of noise. It has been, you can convert it to an algorithm which satisfies these conditions of differential privacy. In fact, it even satisfies the stricter conditions of the local model of differential privacy. There are many connections to learning in the distributed setting or low communication setting and streaming machine learning, both in theory and also in practical applications. It has been kind of very useful in understanding of Valiant's model of evolvability, and more recently in the context of understanding of adaptive data analysis, and that's a talk Thomas gave earlier at this conference. So here we'll be interested in this notion of statistical query complexity. So first of all, let me define it a little more formally. So for the problem Z, which will denote for a statistical problem Z, and a statistical oracle parameterized with this parameter tau, will denote this SQC, statistical query complexity of this problem with this oracle, is the smallest number Q, such that there exists a possibly randomized statistical query algorithm that solves this statistical problem using Q queries for any possible legal implementation of the statistical query oracle. And we'll also look at a slightly simpler definition of just the statistical query complexity of Z as sort of as the smallest Q, such that both the tolerance parameters is lower bounded by 1 over Q, and the number of queries is at most Q. So it makes sense to study this sort of statistical query complexity just for the application of statistical queries to understand what you can do in these models. But here we'll be interested in thinking about this model as some type of proxy for the computational complexity, as I mentioned. And you can think of it as a proxy for computational complexity of solving the same problem using 1 over tau squared samples. And this sort of observation comes from, this sort of view comes from the observations that for most problems that we know, they are statistical query, if we know that they are solvable in time t using n sample, we almost always have also an upper bound on their statistical query complexity within, at most, some sort of polynomial factors. And this basically comes from the fact that many of the known very powerful techniques, such as stochastic convex optimization, various linear threshold algorithms, decision trees, method on moments, and boosting, are all implementable in this model. But on top of this, as I mentioned, it is possible to analyze and prove lower bounds in this model. So the first work, which kind of paved the way towards showing understanding the statistical query complexity, is this fundamental work of Blum and others, who showed that it is possible to understand the statistical query complexity of weak pack learning with respect to of a concept class C with respect to a fixed distribution P over domain of learning. And if you don't really know this model, it's not so important what it is for our purposes. And what they show that there is the following notion of dimension, just to give you an example, in which it's parameterized by the concept class C, the distribution P and gamma, is the maximum number D, such that there exists D function in the concept class of interest, such that for any pair of indices, any pair of different functions, their correlation, when you think of these functions plus minus 1, is at most gamma. So there is a large number of uncorrelated function, and for this notion, they show in this slight refinement from later work, is that this notion of dimension lower bounds the statistical query complexity of weak learning of this class with parameter tau, which corresponds to exactly this correlation, and it also gives a lower bound which is nearly tight up to maybe here square root in the parameter tau, an additional factor. And importantly, it's not just characterized, it's also relatively easy to analyze. For example, you can just look at parity functions, a classical example. And parity functions over the uniform distribution are sort of uncorrelated. Their correlation is 0. So by just using this dimension, you immediately obtain a lower bound for statistical query learning of DNFs, decision trees, and juntas over the uniform distribution. And these are problems for which we don't have any other form of evidence of hardness, and all these lower bounds are tight for the state of the art. So okay, so this is I think it's a really nice, I would say, success story in terms of understanding the complexity of learning with respect to the specific distribution. But the question is, can it be extended beyond this, the weak pack learning? And it turns out now not so easy. So just to extend it to the strong pack learning, but still with respect to the fixed distribution, took sort of a sequence of work which arrived gradually at the more reasonable parameters and maybe also tighter ones. But for a while it wasn't known even if it is possible to, if there exists a parameter, a simple parameter of this type, dimension that would characterize learning of the concept class C in the distribution independent setting, where you don't make any assumptions on the distribution. And even, and in particular, it was also not even known whether this complexity, statistical query complexity of learning on concept class C with distribution independently is equal to the, up to polynomials, to the maximum over all distributions, over distribution-specific specific complexity of learning class C. So, and that's the basic kind of problems we'll be addressing. So first of all, let me define sort of this more general setting that I've been talking about. And to define a general statistical problem, we'll basically use this simple triplet in which this script D describes the set of all possible input distributions that we might be dealing with. Think of it as all possible inputs. Set F describes the set of all possible solutions that from which the algorithm needs to produce an output. And this relation R describes all the valid pairs of input distributions and the output for that distribution. Just as in general, just as in any general definition of the problem, but now we're using distributions as inputs. So this general setting of sort of statistical problems was first considered in a couple of joint works with several co-authors, where we showed some techniques to prove lower bounds on statistical query complexity in this model. However, these sort of the dimensions that the techniques that we have arrived do not actually capture the statistical query complexity. They give you some technique for proving a bound, but it's not the whole story. And the main result of this work that there is a dimension that actually tightly characterizes, and we'll denote it by this SQDIM of the problem Z with parameter tau of the oracle. And what we will show for this dimension is that it is a lower bound on the statistical query complexity of solving the problem Z. And at the same time, it is also an upper bound up to 2 factors, 1 over tau square, which is kind of, again, the tolerance which corresponds to the number sample is usually much smaller than the time, so that's fine. And the second parameter, I refer to it as a sort of a KL radius of the set of distribution, which is roughly the sort of the largest, how flat the family of distribution is, and basically you measure it by picking, minimizing over the choice of the center of the set of distribution, and then looking at the largest KL distance between the center and all the other distributions that you have. And people who work on optimization will recognize it from various guarantees of various algorithms. Okay, so that's the notion. And it's, again, it's kind of useful to know that this radius is upper bounded by the logarithm of the size of the domain. So at most, this additional factor is at most the number of bits that you need to represent your input. But in many cases, it could be just a constant. For example, for distribution-specific learning, it's actually just 1. Okay, so let me now describe you what this notion of statistical query dimension is. And as a warm-up, let me start with a simpler type of problems, which are called sort of one versus many decision problems, in which you are given one set is this script D1, which is a set of distribution. and which we can think of like a positive case, and some reference distribution D0, which is the negative case. And you know that your input distribution is one of those, either in the set or D0, and the goal of the algorithm is to decide which of those. The algorithm just needs to solve this one versus many decision problem. And for this type of problems, we'll define the following parameter. First of all, we'll need this kind of maximum elimination notion, which roughly, okay, it's not so important what the formula is. You will be looking, well, let's say this is the set of your distributions, all in script D. This is the reference distribution. You can think of every query as some sort of projection or as a measurement on the set of distribution, which allows you, by looking at the result of a query on a distribution, you can distinguish between the reference distribution, this D0, and other distributions. So these ones you won't be able to distinguish if you only get a result with an accuracy tau, and the rest you can eliminate. And we are looking at the maximum, the largest possible fraction of distributions that can be eliminated. These are the eliminated one by looking at a single query. Actually, we'll need a slightly more general version of it, which instead of fraction looks at any measure over this set of distribution, and you'll be looking at the value of this set under that measure. And now, having defined this maximum elimination for any given measure, we'll define the statistical query dimension of a decision problem to be the maximum over the choice of all the measures over this positive set of inverse of the fraction that can be eliminated relative to that measure. And it turns out that for this type of problems, this is almost exactly up to some constant equal to statistical query complexity of solving this decision problem by statistical query algorithms, except you need to allow the algorithm to be randomized. It's actually not hard to see why this is true, sort of to see that it's a lower bound. If there is a measure under which no query can eliminate more than a certain fraction, then you'll need a very large number of queries. And for the other direction, you'll just use a duality, and you'll get a randomized algorithm which produces queries that will distinguish between distributions. So now let's go to the more general case. It won't be quite the most general, but it's pretty close to the general case. First of all, we'll be only looking at some so-called verifiable problems Z, and those are problems for which, given a solution, you can maybe using a couple of queries, or maybe just a single query, you can verify that the solution that's a good solution. For example, in learning and pack learning, if you're given a hypothesis, you can check what's the error of that hypothesis just as using a single query. So for this type of problems, we'll define this set B of bad distributions, which are all distributions that cannot pass this verification step for any solution. And now, for example, if you're looking at your problem is pack learning, then the set of these bad distributions when the pack learning with error epsilon will be all distributions over examples such that the Bayes error of this distribution is at least epsilon. So it's not possible to predict it with accuracy better than epsilon. And now, given this definition of this set, we'll define the notion of the dimension to be the maximum over the choice of reference distribution from the set of bad distribution of the problem of distinguishing between the bad distribution and all the other distribution. Again, it's kind of pretty easy to see why this has to be a lower bound. Basically, in order to be able to solve a problem, you need to be able to distinguish between kind of bad distributions and your distributions in the process of solving of this problem, no matter what the bad distribution is. It is more interesting why this is an upper bound, and basically at a high level, and maybe I won't go in as much details, you can convert these sort of decision problems because you can convert into an algorithm which distinguishes between your distribution and any distribution. You can, in some sense, okay, maybe in the interest of time, the way you will convert it to an upper bound, you'll start with some uniform distribution, something very simple, and you'll start solving these decision problems. And what will happen that either you can sort of solve the problem, or you can update your information about the unknown distribution, and the updates will be done using the standard multiplicative weights update algorithm, and we prove that this will give you an upper bound that stated. So let me briefly mention some applications. First of all, we resolve this question about whether the statistical query complexity of learning distribution independent pack learning is equal to the maximum of distribution specific learning, and there we show that they are not. There exists a class of function that is, and that class of function is actually just, they're basically lines over a large finite field, and we show that for this concept class of function, they are, for any fixed distribution, they are easy to learn, but they're hard to learn using statistical queries distribution independently. Another application that we'll show is that the upper bound can be interpreted as some sort of universal statistical query algorithms, and it allows one to derive additional properties of statistical query algorithm. For example, using it, we show some additional simulation of statistical query algorithm in the streaming setting, and we also show us in a different subsequent work, we'll show a simulation using more general types of queries using plain statistical queries. And finally, one additional information, we can use known equivalences between other models such as local differential privacy and models which extract 1 bit per sample to get characterization of these models, although up to, these are much less tight characterization, but still a characterization. Okay, let me conclude. So what I try to convince you is first that statistical query model is a restricted but still a powerful model of access to data. I showed you an algebraic parameters, which is relatively simple and tightly characterizes the randomized statistical query complexity. There are many open problems. Perhaps one of the most interesting is to derive simpler versions of these parameters, which are specific to a given class of problems. So this is a very general one, but we know that in the context of specific problems like weak-pack learning, there are simpler parameters that characterize the complexity. Of course, we need additional analysis techniques, and there are many problems for which it would be interesting to be able to analyze a statistical query complexity, and it still seems not a very easy problem. Okay, well, that's it. Let me know if you have any questions. Thank you.
Yes. Maybe this is too rough of an approximation, but I see a lot of similarities with just minimax low bound for regular statistical problems that are not sequential, reduction to finite to testing, etc. So maybe I'm missing what's the difference here. But for example, why would you expect that when you call the statistical dimension for one distribution is the maximum for all distributions is the maximum of all of them for one dimension? I mean, is there any instance where that ever happens?
That is.
When would you expect that to happen?
Sorry, you mean for the decision version or for the
previous slide?
Okay.
That was theorem on the slide, right?
Why would I expect that this to be true?
What would you expect this not to be true? What would you expect the max to be equal to this?
This almost always, like this is the case with VC dimension. Kind of the star sample complexity, for example, of distribution-specific learning, the maximum sample complexity for a fixed distribution is the VC dimension. And for other models, we know that that's just, that happens to the VC dimension. Like the sample complexity of distribution-independent learning is the maximum over the distribution of a distribution-specific sample complexity.
This dimension is a purely combinatorial object, right?
Sure.
So here you have this statistical, this dimension, which is,
what?
I mean, you called it algebraic, but I don't know if it's geometric or combinatorial. It's something that should actually characterize the class of distributions that you're actually using, right? And somehow there's still some distribution, the statistical query is still entangled in its definition, right?
But what I'm saying is actually it's hard to find examples where this separation holds. So at least I don't know of any other example. So that maybe that's one evidence that it's, for lots of problems, their statistical query complexity distribution independently is at least polynomially related to the maximum overall distribution. Hope that answers, but I'll be happy to continue some other time. Any more?
Okay, so thank you, Vitaly, again.